Okay, so I'll start. So good morning to everybody. My name is Borek Pacak, and I'm from Czech Technical University, and it's my pleasure to welcome you on the second MMP webinar entitled Build Your Own API. As this is a live webinar, feel free to ask any questions during the webinar or during the dedicated discussion session at the end. But if you are not willing to speak, please mute your microphone, as this can help to maintain good sound quality to all. So let me first shortly introduce the MMP project. The goal of the MMP is to develop integrated modeling platform called MuPIF, targeted especially to multi-scale and multi-physics problems. The integral part of the project are two case studies, one focused on modeling processes of photosphore light conversion in LIDs, and other on the modeling CIGS thin film processing for photovoltaic devices. MMP is a part of EU Multiscale Modelling Cluster and has been funded by EU under the 7 Framework Program. For more information about the project, its aims and activities, please visit the project web page, which is shown here, www.mmppproject.eu. The platform design has been introduced in the first MMP webinar on generic platform design, where we have covered the object-oriented design of the platform, introduced the fundamental classes, and presented the platform main features. We have also explained the concept of distributed and parallel model, allowing to take advantage of distributed computing. Finally, the platform installation has been covered as well, including a demonstration using simple examples. In case you are interested, the recording of the webinar is publicly available from MMP webpage. Just follow the link to public events. Okay, so the content of today's webinar, which is the second in a series of 3 webinars, is following. We begin with a short overview of the platform design, followed by the description of application interface, which defines the set of routines and protocols using which the platform interacts with external simulation tools. In the third part, the different approaches how to implement the application interface will be described, discussed, and presented on simple illustrative examples. This part will be presented by Rich Milauer from CTU. In the next part, our partners from MMP project will share their approach and experience in connecting commercial and in-house developed simulation packages to the platform. And finally, we will end up with the discussion at the end. So we start with the overview of the platform design. The platform developed within the MMP project is called MuPIF. It's based on the interacting distributed objects. We have chosen Python language thanks to its fast and efficient scripting capabilities and availability on virtually all platforms. The core of the platform is built on Python language, which is extended by introduction of new abstract high-level classes representing similar entities in our multi-physics or multi-scale modeling space. These classes represent not only simulation tools, but also properties, spatially distributed quantities, solution steps, units, interpolation cells, etc. The platform defines abstract universal interfaces for all these classes. This allows to manipulate the individual instances using generic standardized interface. Such communication with individual objects using a generic interface naturally abstracts and hides all implementation details, including internal data and storage formats used. The fact that also high-level data are represented by classes means that the data exchange between individual applications is done by means of exchanging components or objects and not by exchanging complex raw data. The advantage is that the high-level data representation encapsulates the data and the algorithms operating on the data. So individual applications do not have to interpret the complex data by themselves. They receive the data and algorithms together. Additionally, the platform supports a concept of distributed objects where communication with remote and local objects is fully transparent. The individual objects representing applications or data can be located on different computers, and the method invocation as well as parameter passing is done transparently and securely. So let's move now to an overview of fundamental abstract classes defined by the platform. The abstract application class represents a base class for all classes representing individual models solved by simulation codes. It defines generic methods to get and set data, such as properties and fields, and methods to update state in given solution step, request critical time step, terminate the application, etc. Derived classes represent individual simulation tools. For example, in our project, derived classes represent micros or extreme solvers. We will cover the details of this interface in a few minutes. Field is an abstract class representing scalar, vector, or tensorial quantity with spatial variation. In other words, any variable with spatial distribution. It is assumed that in general, field is defined over a spatial domain, which discretization is represented by another class called mesh, and the instance of this mesh is an attribute of any field. Field provides methods for evaluating its value at given spatial position and getting and setting field values. Property is an abstraction of quantity which has no spatial variation. The method of this class allows to set or get property value, its units, etc. We also have an abstraction for the expression, which is here called function, which can be a function of spatial position, time, and other variables, and can be passed as another type of value to the model. As already mentioned in the field class, the discretization of spatial domain is represented by the mesh class. This class describes the domain as a collection of vertices and corresponding interpolation cells. Derived classes represent different discretization methods such as finite elements, finite volumes, differences, etc. Vertex and cell collections are used to describe discretized spatial domains. Vertices define geometry of cells, and they are in general characterized by their spatial positions. Cells represent a part of spatial domain and provide interpolation services over its volume. The platform, for example, contains implementation of many finite element-specific cell types in 2D and 3D. Time step is a representation of a solution step, keeping target time and time increment as attributes. A class called units represent any unit as a combination of basic SI units. It allows to test for compatible units, provide services for units conversion. And typically, the units are attributes of properties and fields. So this was a short overview of the most important abstract classes introduced by the platform. In the next part of the webinar, we will move our attention to the detailed description of an application interface. But before actually going to details, let me explain what is application interface. Following the Wikipedia, application interface is defined as a set of routines and protocols for building complex software from individual components. In other words, it describes the component like application in our case, in terms of its operations, inputs and outputs. The application interface defines functionality independent of implementation. That's the main point. A good API makes it easier to develop a program simply by putting together all the building blocks using their documented interfaces in a way similar to Lego blocks. So what are characteristics of good API? First, it must be simple, easy to use and understand, and hard to misuse. As you will see further, in MuPIF platform we use simple functions with few arguments and self-explaining names, just to target that point. It should have easy to maintain code. It should be easy to maintain code that uses API. The programming language chosen should be neutral. In MMP we use a Python that can interface with virtually any programming language. And finally, API should be generic and sufficiently powerful to support all and even future requirements. The good API design should be obtained by careful discovery of the problem domain, identifying the necessary requirements in terms of functionality and data dependency, followed by transformation of these requirements into interface specification. The basic requirements can be illustrated on the following figure, which was taken with permission from the book of George Schmidt and Ulrich Kahl on integrative computational material engineering. This figure illustrates a complex simulation chain where the individual blue boxes, for example that one, represent a model of certain process operation on a particular resolution scale. On the vertical axis, one goes through the different scales of resolution for the single process, and on the horizontal axis, the models are connecting in time to simulate the process chains. The arrows indicate the information flow, where for given model operating a selected resolution scale, the initial conditions come from the previous process, inputs come from the lower scales in terms of effective properties and in terms of boundary conditions from the upper level. And similarly, the output represents boundary conditions for the lower scale or subscale models and effective properties for upper scale models. The initial and boundary conditions are imposed via so-called set methods, and they have to be called before the internal state can be updated. The internal state of the model can be updated using the solve yourself method. And after the internal state, which is kept internally by the model, has been updated, the effective properties and other outputs can be extracted using so-called get methods. And this is basic idea of the API design. The typical workflow within the given time step for a particular application consists in setting all the inputs using the set methods, updating the internal state via solve yourself method, and finally extracting the outputs using the get methods. And this can be repeated until the global convergence is obtained. In MuPIF platform, the typical get and set methods for properties are following. The get method allows to extract property identified by property ID, which is being a keyword or sort of keyword, at given time, and optionally for specific object identified by its ID. In case when the property to be extracted is different for different objects of the model. ID may identify specific crystal, inclusion, etc., depending on the resolution level. And similarly, the corresponding set method, shown on the last line, allows to set given property. The type of property, its physical meaning, are the metadata of the property itself, which is passed as a second argument. And basically, it allows to attach the property also to specific object described by its ID, if necessary. So let me have now some general remarks on get and set methods. The get and set methods are not limited to initial and boundary conditions and effective properties, but they can also be used to manipulate or query application state. For example, can be used to set or get convergence criteria, error tolerances, etc. The data passed to and from using get set methods are objects that come with their interfaces. This allows to pass any object implementing property or field interfaces. For example, this allows the platform to support multiple data formats, as these raw data are encapsulated into the object which is implementing the required interface. So its use is fully transparent, because basically only the interface methods should be used for communication with the object. Another consequence of using objects and not raw data is the ability of objects to contain rather reference to data instead of the data itself. This makes possible to include external data such as databases, internet resources, etc. in a fully transparent way. And actually, this is one of the possibilities how to enable interoperability with external resources and even with different platform solutions. And also, in the last point, I would like to mention that the concept of the encapsulation also allows naturally attach additional metadata without breaking anything. The application-specific input, like the spatial discretization, material constants, etc., can be read during the application initialization, typically from the input file prepared by the application expert. The update of the internal state based on the given boundary conditions and effective properties is done using solve yourself method. This update can be done asynchronously if supported by the application, which means that the control is returned to the steering script immediately, and the update continues in a separate process. This asynchronous update allows to take advantage of concurrent processing, and this is, one could say, a typical scenario in multi-scale simulations, where, for example, the individual RVE simulations can be performed independently in parallel. So let me proceed to detailed description of application interface. This abstract interface has to be implemented by all individual applications. This allows to treat all applications using the same interface without being concerned with their internal details. The interface consists of several methods, allowing to steer the application and perform the data exchange. The individual methods are described in the following table. The method definition consists of its name and arguments, and it's shown on the left column, while its description, including type and meaning of all parameters, is shown on the right. The methods are ordered in this table according to their typical use in a workflow, starting from initialization, followed by the set methods, then methods for updating internal state, and finally the get methods. The init method, so-called constructor, is called when the application instance is to be created, and its role is to initialize the application state. This process is highly application dependent, of course, so here it's assumed that the problem description is provided by a domain expert in application-specific input file, which is a parameter of this method. Then there are methods to query some basic application characteristics related to numerical aspects. This includes, for example, methods to query a critical time step, assembly time related to the current solution step, and the method to query the API version if application supports multiple versions. The set methods, which are shown on this part of the table, as already discussed, allow to set initial and boundary conditions as well as effective properties from lower scales. Here we list two typical set methods, one allowing to register a property and the second allowing to register a field. Both methods accept the object representing property or field. Additionally, the property can be registered to particular component of the model using object ID. Full API contains additional set methods allowing to register a function to the model as well. After all external data have been registered using the set methods, the internal state of the model can be updated. The corresponding method is solve yourself. It takes the following parameters: representation of a solution step and two optional parameters, one identifying optional solution state and second optional parameter allowing to run the update operation in background. This means that the execution returns immediately back to the control script. And the control script can query at any time whether the update has been finished. In case of nonlinear problems, the updated state is related only to a local equilibrium of the model, but the global convergence across all the models had to be achieved within given solution step. So the update of internal state can be, in principle, called several times within a solution step, updating the state from given global equilibrium. Once the global convergence is achieved, this state is to be marked as the last equilibrated states. And this is the purpose of the finish step method that serves this purpose. After the update of internal state and achieving the global convergence, the boundary conditions and effective properties can be obtained using the get methods. Here we represent a signature of two characteristic get methods, one for getting the property and second one for getting the field. They take a similar arguments as the set methods. Finally, the application can be terminated using a terminate method, which should terminate application, release all allocated resources, connections, and file. The full API consists of some more methods. We have just covered the major ones, and the full API specification is accessible from the MuPIF documentation and also described in the public deliverable D1.1. Now, we will move to the third part of the webinar, describing the approaches to actually implement the API. And this part will be presented by Víc Milauer. So let me now switch to his screen and so Víc, the webinar is yours.
Okay, thank you, Božek. Hope that you can hear me. Good morning, everyone. So in this third part, I will focus on direct and indirect implementation of API. Just to overview this third part, I will give a very brief overview of API services that Božek has already mentioned, and I will show two ways with direct or so-called native implementation, where we can exchange data by sharing computer memory, and two examples there on a single and distributed computer. And the second mode is indirect implementation, which means that we are sharing data via external data files by reading and writing them on a disk, which is typical situation of several commercial license codes, and I will show example on a single computer. And at the end, I will show very brief sketches how these API approaches were implemented into work packages in our MMP project. So, just to recall what Božek has told about, we have two abstract classes, class property, which represents characteristic value of problem, which is independent on spatial variable. For example, it's a homogeneous quantity coming from the lower scale of RVE. And then we have a field class, which represents some quantity, either scalar, vector, or tensor, which is defined on a discretized domain, and the field is always linked and referenced with a mesh. Of course, each instance may have more fields sharing the same mesh, which is again typical situation in multiphysics formulation tasks. So services in class applications, we have basically three groups. We have set methods where we can set either property, field, or function. And then we have several get methods where we can obtain from the problem what we actually know. And the solve step, which we proceed and solve the underlying physical and mathematical problem. There is a little bit extension in case we are dealing with very large object data. You don't want to copy the whole chunk of data, and it's sometimes enough to copy just the reference to the remote object. And there is a special method, get field URI, which just accesses the reference instead of copying the data. And this is very useful if the setup is run on more computers, with the top level script being run in the middle, and to prevent the copying over the huge chunks of the data across the network. So the data flow between two codes is very straightforward. Usually we are working in some discrete time steps, which means that we have a steering script which calls different services from the code 1 and code 2. So typically we are getting properties from code 1, setting them to the code 2 as, for example, the initial conditions and boundary conditions. Then we proceed a step, get the solution, and the solution can be passed by to the first code, and we can repeat this in a while loop over and over. So this is how API generally works in a multiphysics integration framework. So the first method how to implement this API is called direct, which means that we are directly changing data via memory, and this is the easiest implemented for Python-based code or wrappers, where we can directly call these methods from the Python code. So for example, in the gray box, we have very short code which uses these methods inherited from application class. And by calling these methods, we are getting particular data which are controlled by top-level steering script. So this is a very simple situation, and example 01 demonstrates this. So let's look how it's defined. For example, the application 2 defines the method set property, which obtains the value and accumulates it internally. And by calling solve step, we are, for example, accumulating this property into some average value and counting how many times we called this method. And get property, for example, could mean we are getting the average value, which we just divide the accumulated value by the counted value, and that's what we can return. If you look to the top level steering script, we are calling first some get property method from the first application. That's what we assign to this application number 2. As a set property, we just register the value, calling the solve step function, and getting the average back. And we can repeat this in a time loop. So this is demonstrated in this example 01 as the most simplistic way of coupling two different codes. However, this can be done remotely as well. This is example 02 in MuPIF integration framework. Thanks to Pyro4 module, we can access remote objects in the same way as it were a local object. So the only difference is that the application to instance has to be registered to a name server, which is a computer between two applications. So in a distributed fashion, we just register the application 2 to the name server, which gives back the reference to the remote object. And the rest of the code is absolutely the same as in the case of the local version. So we are just calling particular services, API services of the second application instance. So that's the distributed example. There is another possibility how to implement a direct API. That's through the wrapper codes. Typically, if you want to couple Python code with C++ code, we can expose C++ objects via Boost library and call C++ function directly from Python and vice versa. So just to demonstrate very easily, we need some shared library code. For example, we have very simple C++ code, which returns just some the value, and we can wrap this code using this boost library, creating the module code and exposing the function to be the member of this module. Then the MuPIF API called from Python simply imports this code as a shared library and called the C++ code directly as a getProperty method. Again, we are accessing directly the memory value, so this is the Direct API implementation. So this was the first 3 modes of Direct API implementations. Now let's look how the indirect API implementation happens. This is the typical situation of several license and commercial codes, standalone codes, external programs which are executed from MuPIF MPI. And the difference is that now we have to exchange the data via reading, writing, input or output files to the disk. So typically we have a compiled binary exe file, whatever, which reads and writes data to disk. And for a discrete particular time step, we have to call getProperty. So it means that we are basically accessing not the data in memory, but we are accessing this data. So we have to proceed them somehow and getting these properties back. If you want to set something, it has to happen again through input-output files. So we have to write some file. And if you want to solve the step, we usually call it from the system, it's the code with some arguments, usually getting these input-output files as the arguments. And again, this all setup is orchestrated by a top-level steering script. So that's the basic idea of indirect API implementation. Again, there is example 03 for those who are interested. The difference is in solve step function. So here, for example, we write some initial values to the file, then we call the application. And if you want to get a property out of application, we have to simply read the output file and somehow, for example, read some lines from that file and return it back. So this is the indirect API implementation. The top steering script is likely the same as in previous case. So just to show very briefly examples, there will be 2 speakers later talking specifically about that. So in Work Package 2, there is coupling basically of 4 models with commercial codes, MATLAB console and C++ codes. All of them are using indirect methods, using sort, solve, step, get and set field and properties methods. So this is VP2 as optothermal multiscale modeling and optimization of lighting systems. And in Work Package 3, there are 2 codes, MICRES and Extreme, which optimizes fabrication process of photovoltaic cells, including gas flow, CFD, temperature, crystal growth, etc. There are license codes, and the difference is that now these codes, they may run in parallel, so we can optimize simultaneously more RVs as the underlying problems, again using indirect API implementation methods. And here we are using the job manager to orchestrate the individual processes which run in parallel in the background. So to conclude this direct and indirect API implementation, the biggest bottleneck is support by commercial or licensed codes. Usually if it's commercial code, they don't allow to access directly the data in the memory, so we have to use indirect approach. We are reading input-output data files, and the rest is in favor of direct implementation, because then we can save a lot of time, specific for large data structures which can even exceed the size of terabytes. And then the direct approach it's much more efficient than indirect. However, the bottleneck by the codes itself could be the issue. So that's all from my side, and I will hand the microphone back to Božek.
So thank you, V, for your presentation. And in the next part, our 2 partners representing the Work Package 2 and 3 in our project will describe their approaches and share their experience in interfacing a particular application. In VP2, which is dealing with the modeling processes of photosphore light conversions in LID, and BP3 models CIGF thin film processing in photovoltaic devices. We will start with BP2, which is going to be presented by Oli Tapanian from BP2. So let me switch to his screen. Okay, Oli, the webinar is yours.
Okay. So hello everyone. So my part is to shortly show you how we implemented one of our APIs for the work package 2 modeling of LEDs. So let me start with the description of the kind of the simulation chain. There is kind of two parts or major parts in the simulation. It's the heat modeling and the optical or photometric modeling of the LED. So modeling of light and modeling of heat transfer. And in this part, we are focusing on the optical modeling and the API for that. This is just a more elaborate graph of the simulation with inputs. Maybe I can shortly describe this. So first, if we start from the left, there is scattering and heat transfer are solved in kind of this micro scale, where we solve the scattering of single particles, and in the heat transfer side we solve the kind of the heat or the thermal conductivity of the material from the micro side. And all these parameters are fed in the more macro scale optics, where we do ray tracing and finite element modeling. And from the ray tracing we get absorption, which is a heat source, and that data is transferred to the heat model. So this is how the simulation chain works. As Vid and Borek described before, we have this top-level script that will control the simulation or transfer the data from the APIs. So here we have the three APIs: the thermal model, scattering model, and the optical model. So first what we do is we set properties. So for example, number of rays to trace, or the thermal power at the chip. These are the basic properties of the kind of the problem. Then we get absorption field from, or kind of field of the absorbed power from the thermal model, which gives us actually the finite element mesh that is made by the thermal model. In the scattering model, we do not need any mesh, but we need the mesh to set the absorption data to that. So that is done next. And these are done with those get and set methods for fields. Then we will use the solve step for the MIE API or the scattering model and let it run. This will be done synchronously, so we have to wait for it to finish. Then we will get the scattering properties from the model, scattering model via get and set method and put them to the ray tracing optical model. After that, we do the corresponding solve step for the optical model, and this is also a synchronous process, so we have to wait for it. And after it finishes, we will have the updated absorption field that we can set back to the thermal model. And after all this, we can call the solve step for the thermal model. Now we are in this, we are using our in-house ray tracing software, but in principle this could be done with commercial software such as Light Tools, which has their own API on top of which we could implement the MuPIF API. This is just some information about the ray tracing API. Maybe interesting here is that the size of the data we move between the thermal model and the optical model, it can be large or small, depending on how accurate we want to be and how many, for example, rays we trace. And also that this is indirect implementation of the API, and so we use data files. This is kind of summary of the API, what is done, but I can maybe explain it better with this code example here. So first, this is the top level script. So what we do is we follow the graph, what was before the block graph. So we first get the absorption or the heat source volume field from the thermal API and set it to the tracer application, which is the ray tracing API. After that, there was the solve step from the scattering API, which is called here the MIE app. And then after the solve step has finished, we will get a property that is related to the scattering probabilities, which is needed by the tracer ray tracing app, and which is set using the set property. As you can see here, here is the object IDs are in a separate file, so they are called op ID, op particle type 1, for example. After that, the tracer app solve step is called, and we set also the background running to false, so that we have to wait for the tracer app to finish tracing. And after it has finished, we will transfer the field back to the thermal app TNO. So we use again get set fields, and after all that we use the thermal app to solve the heating for the LED. And then we plot some results from the TNO app. So we use again get field, and we get the heat source, volume, and transfer or write it out in a visualization toolkit data format, which can be visualized by another software. And in this slide, I show a kind of simplified version of our solve step from the Tracer API. So inside, what happens inside the solve step of the Tracer. So we first have to check whether we have all the fields and properties that we need for the tracing. This is done in a different function, but it's here kind of just shown the call. Then what we do is we write an input file for the ray tracer, which is JSON format in this. And after that, we prepare for running the tracer outside of Python using sub-processing module of the Python. And since we want to also be able to run the tracer in background, we need another kind of thread to start the background process. This is why this looks kind of odd, but that is how we do it. After now, when we start the process in the self.postthreads.start, we then return from the solve step, and if the run in background is set to true, we return from the solve step. And after the run is complete, this kind of tracer process ended function is called, in which all the kind of post-processing happens. So we read back the data files from, for example, from the absorption and convert it to MuPIF compliant format in the field and in the mesh. Then here is a slide of visualizing the results, what can get from the simulations. So on the left-hand side, there is the temperature field visualized in kind of this mesh. And on the right side, we have the trace rays. And I think this was it from VP2 example.
So thank you, Ori, for your presentation. And the second speaker is Ralph Alterfant from Access. And so now let me switch to this screen.
Yeah, hello everybody, and again, this is Ralph from Access, as Borg introduced me.
Okay, we can see it, Ralph. It's fine.
Okay, I represent the next work package, is work package 3, and we try to model a 6-component, a photovoltaic component in a salinization process, fabricated in the salinization process, and our simulation chain targets to predict the microstructures which are evolved, and to give a kind of quality factor how good is the salinization process for the photovoltaic element. We are staying on a continuum model level in the simulation chain, and starting here on the right side with a macro simulation CFD software called Extreme, provided by our partner Selvian Glass and Solar from the Netherlands. And this macro simulation passes temperature profile to the microstructure level, which will be a thermodynamic and phase field model evaluation of the microstructure. It's done by a micrist provided from our side, from XSDV, EV from Aachen in Germany. And the coupling back to the macro simulation will be done in a homogeneous JSON routine, which get as an input the concentration of the elements in the time step and phase field distribution. And this part will be done by TNO, and this is under development now. And what is given back is a measurement of the surface reflectivity of the element at a single micro location. It's macro location, so a single point in the macro location. And what is done is an averaging over several points. In my description here, I will focus on the micro side only to get it more clearer and to speed it up a little bit. What is done in the top-level script is the usual setup and workflow and finalization, as we've seen in the descriptions before. I detailed the setup process here. The target is here to get an object handle for the application interfaces. So we connect to a name server and allocate a job and get back a handle of the application service, the application interface. And we have the opportunity to upload input files to probably a remote server where the application interface runs. The workflow you have seen now several times. It's about set all properties you need for running the simulation. In our case, it's a macro location to distinct several macro points and a temperature. Then we start solving with micros with the soft step routine, and wait for the results and get a concentration profile of all elements as an output. This will be passed back to homogenization, and then the next step in the macro location will be done in the macro simulation. After they're done, the whole time loop, the whole simulation chain, some finalization is necessary, and that is mainly of freeing resources. Here is a rough overview of the specification of the microcode. It's continuum model type. It's running on Windows and Linux. I will skip the details here. What is interesting and what you should get from this slide is what kind of files has the interface to handle and what kind of data. So we use an indirect API implementation via files, and the input is necessary for Micros is just a parameter text file, which we first pass a template to the interface, and then enrich it with the special properties for several time steps. That is a macro location and a scalar value for time and temperature. So it's the target time of the next simulation step here. The output will be a short vector of element concentration, and can also be everything Micros produces as output. So several fields of phase fractions, local phase distributions that can be in the range of a few megabytes up to gigabytes. It depends mainly on the resolution and how many fields are integrated here. So it takes, in our simulation chain, in the first test, about a quarter of an hour to half an hour per time step. So it's good to do it in parallel and solve several macro locations in parallel. The usage of the interface is quite straightforward here. So constructor and getting some information with the signature of the application is quite easy to understand. The special trick I want to explain here is setting the property which modifies the state of the application interface. So here the location, the macro location, is just for running several distinct Micros simulations. This property has no meaning for the Micros input, but is only to switch from one simulation to another. The normal properties which will enrich the input files for the simulation can also be set by this method set property. So it's temperature mainly. Then we solve the step. And this is, in the case of Micros, always a non-blocking call, so it will be run in the background. And that gives the opportunity to steer another application interface and to run several evaluations for several macro locations in parallel. Of course, it's an asynchronous call, and we have to wait for the results now and get back properties and fields for elevation and passing to the other macro simulation, passing back. So that's all. I choose for more detailed description the get field method here, because I want to focus on not steering Micros, but what are the problems to identify the results and how much data has to be passed. So Micros stores this simulation results in a VDK file, and there are all fields, all results included for one time step and one VDK file. So I will go roughly over the procedure, how the special file can be found for simulation. You can look it up in later. We have to find a match for the requested time step in the list of VDK files, and then the most interesting part is just one line. So it's from the PyVDK package to read the whole VDK file in the MuPIF framework or in the interface, and that can be can be a few megabytes or a hundred of megabytes for one-time steps. So here it has to be taken care of. Then the next step for the MuPIF framework is to set up the mesh topology. So setting the dimensions and the point coordinates for an unstructured VDK mesh. And then this routine from the MuPIF framework will set up the topology, and we have to fill it then with a special data from the VDK file here. It's the phase field, which will be put in this field object of the MuPIF framework. And the next step is also this little line, which will steer a possible remote data transfer and pass the field object back to the top level script. And that can be a remote data transfer of megabytes or more. WIT formally introduces this get field URL routine, which allows to pass directly from one application interface to another, and without interaction of the top level script. That will save a lot of time, I think. So that's nearly all from me. What you get back at the top level script is, for example, here on the left, a macro temperature profile, or you can see on the micro level the phase distribution, the local phase distribution of the evolving phases here for one time step or for all time steps. So that's work package 3. And
okay. Thank you, Ralph, very much. And before we move to the discussion, I just want to announce the last webinar of the MMP project. So let me switch to my screen. So, okay. I just want to announce this third MMP webinar, which is entitled Perform a Platform Run. The preliminary agenda for this webinar is following. We will first cover the platform installation, then introduce a selected sandbox problem that will be used to demonstrate the live platform run, describe the workflow script of the sandbox problem, and finally show the live demo by running and monitoring the sandbox simulation. The webinar is planned to take place in May this year, and the exact date will be announced in advance on MMP website. So okay, now we are coming to the last point of today's agenda, which is the discussion. So if you have any question or comment, you are free to ask. Maybe I have one question to Ralph. Ralph, could you just guess what's the ratio between the computation and actually the data transfer within the microS and the steering script?
I think it's about 1% for data transfer. So
okay.
So the simulation depends. You can run a quarter of an hour or 1 hour. Mm-hmm. So it's a big part, the external simulation.
Okay, thank you.
That's another point is that for extreme the ratio is a little bit different. So in our test case now, extreme runs about 1 minute, and the percentage is high.
Okay, I see. Thank you. Any other question? So if not, let me finally thanks to all of you for joining us. And in case you are interested, the webinar has been recorded and the recording will be available soon on MMP site. So thank you very much and have a good morning. Goodbye.
Goodbye. Thank you. Bye.
Bye-bye.
Bye. Thank you very much.